Okay, welcome to the second lecture in the series of these special important topics and complex topics lectures of the subject digital signal processing. Here I will be discussing about design of infinite impulse response filters. So, filters are basically used to change one or the other part of a signal, and for designing filters generally the representations that are used is that in digital systems impulse response is generally used. So, impulse response is denoted by small h of n. So, this is the response of the system when a unit impulse is provided. If I take the Fourier transform of impulse response, we get capital H of e j omega, which is said to be the frequency response of the digital filter. If we take the Z transform, of the filter, then in that case what we will have is capital H of Z. So, capital H of Z is either taking Z transform of impulse response or evaluating the filters, the frequency response of the filter at e raised to the power j omega, that is Z is equal to e raised to the power j omega. And if we talk about analog filters, for any analog system, that the denotion is in terms of Laplace transform of impulse response for a continuous time system. So, basically we should be aware that we are designing infinite impulse response systems, IIR filters. These are IIR filters, infinite impulse response filters, the designing of which is not done directly in digital domain. We generally first of all perform the designing process in analog domain and then convert the analog filter into digital filter. So, finally what we should have is H of Z. H of Z is corresponding to the specifications required for a digital filter in frequency domain, and therefore capital H of e j omega is the specification. And firstly what we will design H of S. So, our procedure is very simple. We design H of S, we convert H of S into H of Z, which is set analog filter is converted into a digital filter. Okay, and the requirements that we have we are generally given is in terms of frequency response. So, frequency response gives the requirement specification of the filter and we design. So, in frequency specifications, what we generally have is a characteristic like this, non-ideal characteristic like this, capital H of e j omega. It is DTFT and therefore it is periodic between minus pi to plus pi. Since it is a real filter, real impulse response, whatever is on the positive side will also be on the negative side. So, we have a certain gain allowed in pass band. So, omega p, in omega p, or I should rather write this omega because our representation is for analog, up to which the frequency magnitude can come from 1 to say delta p, and a highest pass given delta s till omega s. So, this is the stop band frequency. So, a specification is generally in terms of these 4 parameters: the pass band frequency, the pass band allowed magnitude response, how much from 1 we can come downwards. Similarly, the stop band cutoff frequency and how much attenuation it is required beyond that. So, how much attenuation means how much smaller the magnitude becomes after omega s. So, in order to meet these specifications, we firstly design analog filters. The analog filters that we are mainly concerned in this lecture is Butterworth or Chebyshev. And after designing these filters, designing means evaluating capital H of S, we make capital H of Z converted into capital H of Z. So, that conversion can be done either using impulse invariant method or bilinear transformation. Now, in impulse invariant method, it is a direct mapping between S domain and Z domain. So, these are the 3 relationships for a simple pole and for complex poles, which are generally used to convert S into Z. This is basically H of S converted into H of Z, and this is generally done based on this mapping. This is the mapping that is used, that z becomes e raised to the power st, and according to this what happens is that the left hand side of the S plane maps directly into the unit circle. That means that a stable system is mapped in a stable system. A stable analog system is mapped on the stable digital system. Another transformation that we used is BLT, bilinear transformation. Bilinear transformation, again the analog frequency can be directly taken from the digital frequency using this relationship. This is pre-warping that is done. So this is digital, or I should rather write discrete frequency, and S can be replaced by this relationship 2 upon T 1 minus Z inverse divided by 1 plus Z inverse to obtain H of Z from H of S. So again using this we can convert H of S into H of Z, and here T is the sampling period which must satisfy at least the Nyquist criteria. Okay. So the filters that are there that are generally used is either Butterworth, Chebyshev or electrical. These are all pole filters. So all pole means in the numerator we generally have a constant, not one, basically it can be any value, a constant, and it is all pole means whatever the values of S are there in the denominator. So firstly, what about the Butterworth filter? The Butterworth filter is designed using the frequency response given by this relationship. Remember that this omega is for analog systems. So magnitude square of H j omega is 1 upon 1 plus omega by omega c raised to the power 2n. So which means 2n is the number of poles. So 2n is the number of total poles, and omega c is the cutoff frequency. So for designing these filters, again the specifications will be given, the passband cutoff frequency, stop band cutoff frequency, passband attenuation, stop band attenuation. But what we will require to design these filters is only two parameters. First is the order of the filter and the 3 dB cutoff frequency of the filter. So if we can obtain these two things, we can directly write the capital H of S. So this mathematics is very simple. If we see the construction, the poles actually lie on a circle having a radius omega c, and there are 2n poles. So basically 2n poles means some set of poles are here and remaining n are here. So this means that in total the complex conjugate, the multiplication of HA of S and H minus of S should be according to the frequency relationships. We just replace omega by S by J. So we will get this, and therefore the pole can be directly defined as S is equal to plus minus J omega c e raised to the power J 2k minus 1 pi by 2n, where this k is between 1 to n, is between 1 to n. So using this we can evaluate the poles. If we have the poles, we have the transfer function. So like for a few orders we can use this to implement a transfer function. So suppose I just look at this expression, it is e raised to the power j theta. So I can replace it cos theta plus j sin theta. Then I can take the j inside and multiply, so it becomes minus I, the real part becomes minus I, and cos becomes the imaginary part, and there are n conjugate pairs, and the one simple pair is at omega c. So basically there are n minus 1 by 2 complex conjugate pairs. These informations are required to write the Hs directly. We will see subsequently how it is done. Suppose for the case of n is equal to 1, for the case n is equal to 1, using this relationship, this Sk, since there is only one pole, S1 will be sine and pi by 2. Pi by t how? By k is equal to 1 in this. So if I put k is equal to 1, I have pi by 2 and cos pi by 2, which becomes 0. So we basically have S plus S by omega c plus 1 is equal to 0. So our transfer function becomes, this is H of S. So H of S is omega c divided by S plus omega c. So this is Butterworth transfer function for first order system. Similarly, I can do the same thing for n is equal to 2. I will put k equal to 1 and 2 in that, and I will have a complex conjugates, which means I already have 1 and 2 directly, and therefore the suffix are S1 and S2. This is S1 comma 2 because 2 poles directly we will have from the formula. If I take this complex conjugation, I have capital H of S equal to omega c square, S square plus square root 2 omega c S plus omega c square. Again, if we go for 3, we will have h of s is equal to s plus 1 and s square plus s plus 1. Just look at the expressions which are arriving. For n is equal to 1, we have s plus omega c. For n is equal to 2, I have a quadratic here. For n is equal to 3, I have a simple pole, and then this will always be normalized by omega c to give this. So it is for n is equal to 3, and it has one simple pole also. It has one simple pole also. So I can now directly write the formula to provide the transfer function of the system. The transfer function of the system can be divided in two parts. First is when n is even. If n is even, we have seen that it will be omega c raised to the power n, the transfer function hs we can write directly, and continued product, pi means continued product, k is equal to 1 to n by 2 s square plus bk omega c plus omega c square. So once we have evaluated the order of the system, the cutoff frequency of the system, we just need to define something which is called bk. bk is defined as 2 from this derivation, 2 sine 2k minus 1 by 2n. So we just have to evaluate where k is from 1 to n by 2. If we just have to evaluate bk, and we can write the transfer function for even. Similarly for odd. For odd, we have seen that there is one simple pole at minus omega c, and remaining quadrature poles that will be n minus 1 by 2 times. So continued product of s square plus bk omega c s plus omega c square and omega c raised to the power n. So we can directly again write the transfer function of a Butterworth filter, and we have already seen if we can write h of s, we just need to convert it into h of z, because h of s has been designed using the specifications of the digital filter. Like for example, and also we require n and omega c. So how can I evaluate? So our basic relationship of frequency transformation is this, that mod h j omega square is equal to 1 divided by 1 plus omega upon omega c raised to the power 2n. So what we require is n and omega c. So for that I can use this information, because this is nothing else but mod h j omega, with respect to omega. So what I have is that at omega p, the transfer function's magnitude becomes del p. Similarly at omega s, it becomes del s. So I can use that in the expression. In place of mod h j omega square, I can write del p square, and I can just substitute omega replaced by omega p. So here, if I go on and solve, I can have the values for omega c and n. So if I go on and evaluate, I will have 2n is equal to log, because these are two equations basically, one evaluated at this and one evaluated at this, at omega s and omega p. If I divide both, we will have this expression, because these two you can also equate, but if we just divide, then this will be this ratio on the left hand side, and on right hand side this will be the ratio. So our basic expression will become 1 upon del s square minus 1 and divide by 1 upon del p square minus 1 is equal to omega s by omega p raised to the power 2n. If we want to evaluate n first, I can take log on both the sides. So this will come 2n, and our final expression will be this 2 comes here, which will become a square root. So the order of the filter is square root 1 upon del s square minus 1 divided by 1 upon del p square minus 1 divided by log of omega s upon omega p. Everything here will be the part of the specification. So if I have the specification, I have the order of the filter. Once I have the order of the filter, I also have the cutoff frequency, because the two are related by this equation. You can put in either of the equations. There were two equations here. I can use either of the equations. I am using the first one. So according to this, the cutoff frequency is omega p divided by 1 upon del p square minus 1 raised to the power 1 upon 2n. So once I have evaluated n using this formula, I can put the value of n here. Since omega p and del p will be in the specifications, I can calculate the cutoff frequency of the Butterworth filter. So as an example, suppose del p is given as minus 2 dB and del s is given as minus 10 dB. Also understand that all of them will be negative, because 1 is the magnitude reference value. So anything below 1 will be fractional value, and log of fractional value will be negative. So passband ripple that is allowed here is minus 2 dB and stopband is minus 10 dB. And cutoff frequencies for passband is 20 radians per second and omega is equal to 30 radians per second. All are given in analog, and therefore no conversion is required. So if I just convert these into linear scale, this will be delta p is equal to 10 raised to the power minus 2 upon 20, because this is voltage. It is 20 log to the base 10 of x. So therefore it comes out to be 0.794 and it is 0.316. If I use the formula for n, I am getting something which is more than 3. So we'll always satisfy the passband more, and therefore we'll take the higher order, just one more. The integer order has to be integer, the next integer. So next integer is n is equal to 4. So if I have n is equal to 4, I can calculate the omega c, which comes out to be 21.387. From the values in the numerical, if the passband cutoff frequency is 20 and the stop band is 30, the cutoff has to be in between, the 3 dB has to be in between, and it is coming to be in between. And since n is 4, which is even, we can use the formulation for n even. For n even, the formulation was omega c raised to the power n, k continued product 1 to n by 2 s square plus bks omega c plus omega c raised to the power 2. Means there will be two factors. N by 2 means 2. So k is equal to 1 to 2. So two quadratic factors, and b1 and b2 both will be required. So I can just take the formulation for bk, which was I think 2 sine 2k minus 1 pi by 2n. So I can just put k is equal to 1 and 2, and we have b1 is equal to 0.3824 into 2 and 0.9207 into 2. Two factor is coming from this. So that has been written exclusively. So if I can use this formula, omega c has already been taken care of. So the HS, the analog filters frequency response, will be omega c raised to the power 4, first quadratic and second quadratic, corresponding to b1 and b2. Now I can always convert this back into digital domain, either using impulse invariant transformations or bilinear transformations. So that can be used for IIR filter designing using Butterworth filter. Secondly, there is also something which is called a Chebyshev filter. For Chebyshev filter, the numerator has a different constant a, and the HS is given by a divided by 1 plus epsilon square Cn square omega upon omega p. Understand that this is a function of omega, and Cn square is the Chebyshev polynomial. So Cn square is defined as of x is defined as either it can be cos of n cos inverse x for modulus of x less than 1, or it can be cos n cos inverse x for magnitude greater than 1. So using this, again from the numerical side of point of view, the specifications will be given, the passband cutoff frequency will be given, the passband magnitude will be given, the stop band cutoff frequency will be given, and minimum attenuation in the stop band will be given. So based on that and some numerical computation, the epsilon can be derived to be a square root of 1 upon del p square minus 1. Just relate this to what we discussed in Butterworth. The formula is similar looking, and n, that is the order of the filter, can be again computed using cos inverse 1 upon del s square minus 1 divided by 1 upon del p square minus 1 divided by cos inverse del s upon del p. So you can just relate this with the Butterworth formula for n. It is just that here there are log, the same thing is there. It is basically omega s upon omega p, and 1 upon del s square minus 1 upon 1 upon del p square minus 1 and a square root. So only the factor that changes is the log in Chebyshev. So the formula for n is similar to that, and we'll take the next integer, therefore the sign greater than or equal. So if we go like that, for odd, the formulation is for transfer function, writing the transfer function directly, we have omega p raised to the power n, that was there also. Here there is no cutoff frequency, the only two things that are required is n and epsilon. Remember, we only require n and epsilon in Chebyshev. There is no cutoff frequency omega c. So what frequency omega p will be used for definitions. So omega p raised to the power n c naught, and continued product from 1 to n minus 1 by 2 and ck. We'll define ck and c naught. And if it is odd, there will be a simple pole, but just that to make the DC component 1, there will be an a c naught factor here. And since it is odd, the continued product goes from 1 to n minus 1 by 2 again, and a quadratic factor s square plus bk omega p s plus ck omega p square. Just because in the transfer function we had a, we want the DC value to be 1, and therefore other coefficients which are ck's have been introduced. Ck's are only introduced to make the DC constants, DC value to be 1. The transfer function has to be 1 at s is equal to 0, which implies s omega is equal to 0, which implies frequency 0, which implies direct current. So at DC, the transfer function has to be 1. So for odd, we can directly write the transfer function using this. For n is equal to even, we can again use the same formulation, just that in case of n is equal to even, there will be one more factor of 1 divided by 1 upon epsilon square from the transfer function to make the DC component to be 1. And again, it will be omega p raised to the power n. Continued product will now be from n by 2 and again n by 2, not n minus 1, it will be n by 2 and ck and 1 upon 1 plus epsilon square. So this will be again the continued product of these entities. Now, how do we define the coefficients bk and ck? So first of all, we calculate what is called the epsilon. This is epsilon, yn, and which yn is also equal to y naught. So yn is 1 upon 2 square root 1 plus 1 upon epsilon plus 1 upon epsilon 1 by n and the same quantity raised to the power minus 1 by n. So this is yn. If I have yn, then this yn is actually equal to C0. C0 is for the case of n odd. So C0 is equal to yn and ck will be evaluated as yn square plus cos square 2k minus 1 pi by 2n, and finally the bk will be 2 times of yn sine 2k minus 1 pi by 2n. This is 2 yn sine of 2k minus 1 pi by 2n. So you can see the similarity. The sine portion is still there, the 2 portion is still there. It is just yn that has been compensated for, and that yn at is also equal to C0, and ck's can be evaluated using cos square plus yn square. So if I have all this, I can directly write the transfer function of the Chebyshev filter for designing the infinite impulse response filter. Suppose that omega s is 50 and omega p is 20 radians per second. I want to design a Chebyshev filter where the passband attenuation is 2.5 dB at omega p and stop band is 30 dB. So again, delta p we can evaluate using 10 raised to the power. 10 is corresponding to 10 is from the base of the log, and the 2.5 is the attenuation that is allowed. So minus 2.5 by 10, this will give me delta p. Similarly, delta s will be 10 raised to the power minus 30 by 10, because at attenuation omega s, which means after omega s, the minimum attenuation that is required is 30 dB. You can have more attenuation, means lower magnitude values. Minus 31 is allowed, but minus 29 is not allowed. So according to that, delta s comes like this. If I have omega p, omega s, delta p and delta s, I can calculate directly what will be the epsilon, because I only require epsilon and n. I require two quantities. So epsilon is equal to 1 upon del p square minus 1. Del p we have evaluated. So epsilon comes out to be 0.88. That is the eccentricity of this filter. And the order of the filter can be computed using cos inverse 1 square root of 1 upon del square minus 1 and divide by 1 upon del p square minus 1, and cos inverse del s by cos inverse omega s by omega p. So that comes out to be 2.09, which means that it is n is equal to 3. We will take the next value to satisfy the passband. If n is equal to 3, I can evaluate what is C naught, which is equal to by the formula that we have used for in terms of epsilon, and cos ck is yn square plus cos 2k minus 1 pi by 2n, which comes out to be 0.854. Remember, since it is 3, if I can write, I will have a numerator and I can have s plus omega p into C naught, and I will have a quadratic part here. So therefore, I only require one ck. We also require a bk, so only one bk is required, and that will be 0.32185, and the value of C0, which is yn, is computed as using the value of epsilon in the last slide. Value of epsilon was approximately 0.88. So if I put a 0.88 here, it just depends on 0.88. It will give me 0.32 and then the remaining values. I can just put all the values in the transfer function, and I can use the formula for n is equal to odd. So for n is equal to odd, in the numerator, I have passband cutoff frequency omega p raised to the power n C naught, continued product from k is equal to 1 to n by 2, n minus 1 by 2. Remember, in this case, we have n is equal to 3, and therefore n minus 1 by 2 becomes 1. So basically, there is no continued product. There is only one C1 Here will be only C1. Similarly, there will only be one C1 here, and there will be only one B1 that we have defined in the previous slide. We can just substitute all the values and we can have the transfer function of the analog Chebyshev filter given as this 21.89.6 divided by S plus 6.4, S square plus 6.6 S plus 343.2. So if I have the specifications of the filter in terms of passband attenuation, stop band attenuation, passband cutoff frequency, stop band cutoff frequency, then I can always design the transfer function of the analog filter. Once I have designed the transfer function of the analog filter, I can simply convert it into Hz using either impulse invariant or bilinear transformation. Also, in case of bilinear transformation, before going for omega p and omega s, we will have to convert omega p into omega p and omega s into omega s. So in discrete time domain. So using pre-warping we do that. Therefore, BLT is slightly more complex in that context, but it is better because the mapping is one-on-one mapping. In case of impulse invariant, the mapping is many to one. That is the main disadvantage of impulse invariant transformation. So we can always compute h of z. But the content of this lecture is towards designing the analog filter that can directly be converted into an infinite impulse response digital signal processing filters. Thank you.